Chapter. I can't possibly live up to that. So let's instead talk about this guy. This is Arthur Samuel. Arthur Samuel's famous for a number of things. He's famous for being a very bad player of checkers. He's famous for making IBM's share price go up by 15% in one day. He's also famous for being the first guy to conceive of the possibility of a future of personal computers. He's also the father of machine learning. In 1956, being such a bad checkers player and wanting to write a program that could play checkers, he found himself in the difficult position of not being able to program in those rules because he didn't know the rules themselves. If he did, he could be a better checkers player. So rather than giving up, he tried something very interesting. He gave the computer a general sense of the kinds of ways in which you could describe strategies for playing checkers, and then he had the computer play against itself thousands of times. And as it did so, it tried to figure out which are the ways that it was doing things that worked better than others, and it could teach itself to play checkers. And it turned out that it worked. It worked so well, in fact, that Arthur Samuel's checkers playing program could pretty soon beat Arthur at checkers. In 1956 then, Thomas Watson, the then CEO of IBM, announced to the market that this had been done, and that day, IBM's share price increased by 15% on that announcement alone. So the commercial and financial impact of machine learning is certainly not new. And in fact, by 1962, this checkers playing program had taught itself to be so good that it beat a state champion in the US. That's 1962. Also in 1962, Arthur Samuel predicted in an essay not as well known as it should be, that one day in the future, we will all have computers on our desktops. In fact, he predicted this would be in 20 years' time, so 1982. So I guess he was about 10 years too optimistic. He also predicted that in the same time frame, we will not be programming computers anymore. We will simply be telling them the kinds of things we want to do and giving them examples, and they would be figuring it out. Was he wrong, or was he just very optimistic? And I would say, actually, he was just very optimistic time-wise. In fact, replacing rule-based systems with systems that learn from examples is exactly now what is starting to happen. The craft and science of programming, I think, will become less and less important, and it'll make all of us effectively programmers because we can tell computers what we're trying to do by giving them examples. We're already seeing this a lot. For example, when you use Facebook or LinkedIn, it almost creepily knows who your friends might be or which connections you might want to add. And that's because no one programmed in the rules to say this is how you figure out this person's friends, but actually this has been developed with machine learning, a system of using pattern recognition to figure this out. So when you see a computer behaving almost creepily smartly, you can guess that machine learning is somewhere behind the scenes. We also see this with Watson, of course, and Watson is really built on a number of layers of machine learning, along with a lot of curated knowledge. It's also making a huge impact in industry. For example, this is an example from Allstate, America's largest insurer, whose algorithms for predicting claims were improved by 270% as a result of using machine learning. Now, I'm particularly familiar with this because I was previously president of Kaggle. Kaggle's the company which my friend Neil Jacobstein mentioned earlier today. It runs competitions, global competitions, to see who can come up with the best predictions. And Allstate ran one of these competitions to see who could most accurately predict the claims for millions of insurance applicants. The winning algorithm is the one that you see in this chart, which is 270% better than the one that Allstate had developed internally, and they have one of the top teams of actuaries in the whole world. So it's not that they had a difficult task. It is that they had a difficult task to beat this group. It wasn't simple at all. So this is the impact that we're seeing right now of machine learning in industry and in science. It's something that you're all seeing now every day. Now, I've been in this industry for over 20 years, In the early days, I would have to describe what machine learning could be. It was quite challenging. Now you're all using it. It's a lot easier. But what I want to do now is to describe what you can't see because it's still hidden away in academia, and this is what's going to happen to you in the next 3 to 5 years. I'm going to start this story with another Kaggle competition called the Merck Molecular Activity Challenge. It doesn't sound very exciting, but actually this was about basically automatic drug development, and specifically figuring out which molecules will turn out to be toxic using a machine learning algorithm. Merck and other pharma companies have invested billions in this area. It's called chemoinformatics, and it's a vitally important area for healthcare. Interestingly, this particular competition, like in fact every Kaggle competition, when it was won, it turned out that the winning algorithm was far better than anything that had ever been developed in academia or industry before. What was really interesting is that the people that did it were led by this guy, Geoffrey Hinton. Now, for those that are concentrating, you might remember that Neil Jacobstein introduced him earlier today as being the guy that invented this field called deep learning. Geoffrey's team spent 2 weeks. Nobody on the group had any background in biology or life sciences, and in those 2 weeks, this team created an algorithm better at identifying and predicting the toxicity of drugs than anybody in the pharmaceutical world had ever before. How did they do it? They did it, again, not by creating the rules or by talking to domain experts, but by automatically learning from data. And specifically then, we're talking about this whole area called machine learning again. More specifically, they used this algorithm called deep learning. Now, deep learning is an evolution of the neural networks, which a lot of you probably heard about 20 years ago. Now, a lot of you are thinking, oh yeah, I heard about those 20 years ago, and they were kind of a disappointment. They were. We weren't quite ready for them yet. But folks like Geoff Hinton have been working on them ever since, and this was the point when I realized that I had been ignoring this field at my peril, because suddenly it turns out that these guys had built the world's best drug discovery algorithm in 2 weeks, and nobody on the team had any domain experience in pharma, biology, or anything at all. So this was when I realized that this was going to be critical. In fact, since this time at Kaggle, deep learning has rapidly become the most successful algorithm across competitions in many, many different areas. For example, in a competition to try and identify parts of a tumor that were most aggressive, areas called areas of mitosis, are based on these pictures here. These green arrows are pointing at the areas which a team of 4 expert pathologists agreed together were areas of mitosis. It takes 4 pathologists because no one is good enough to do it themselves. It's so hard that to do this properly, multiple pathologists are each given these breast cancer slides, and they independently mark them up and say, I think these are areas of mitosis. The world's best pathologists agree with each other about half the time. A machine learning algorithm based on this imagery was trained to try and recognize these areas, and it turned out that it agreed with the group of pathologists 60% of the time. So this was in the same year as the Merck challenge, and this competition showed us that in fact computers have now got to a point where not only can they recognize images, but they can recognize very sophisticated images better than experts who have been trained for decades to look at these exact images. So clearly something extraordinary is going on. One of the challenges here, though, is that actually trying to get these kinds of labeled images of saying this is an area of mitosis or this isn't, or trying to get a picture of like this is a dog or this is a cat or whatever it is you're trying to do is challenging. There just aren't that many labeled images in the world. So Google, in the same year, this is all in 2012, announced that they had done something really interesting. Many of you have probably seen these pictures already. Instead of getting a whole bunch of labeled images, they simply pointed a deep learning algorithm at YouTube. And they said to YouTube, they said to the deep learning algorithm, okay, here is YouTube, watch these videos, and build a deep learning network to try and find stuff, find whatever you want to find. And they then went back and looked inside that network architecture, which had something like 600 million neurons, and looked at a couple of neurons to see what they had discovered. And these are two examples. The one on the left, clearly a person. The one on the right, if you squint a bit, you can see clearly a cat. So this deep learning algorithm, just by watching YouTube, had discovered the existence of things like cats and people, and in fact also buried away in these 600 million neurons is just about every other concept you can imagine. Indoors versus outdoors, vehicles, wheels, legs, and so forth. So Google went on to actually then take these features and use that to try and do something useful. And so they decided to see if they could improve Google image search. And the results you see on the screen here are the results of taking these learned features and then on Google image search saying, can we use those to try and guess what these things are pictures of? And as you can see, every one of these images, for example, it has figured that out correctly. Now, in some ways, this doesn't seem that smart. We can look at this and we can say, oh, I know that's a seatbelt, I know that's archery. It's not hard. But in fact, in 2012, these were exactly the kinds of things that humans were much better at than computers. So as you can see, this is an area that's now rapidly changing. And in fact, now it's not just images where this is happening. Another place where humans have traditionally been much better at machines is reading natural language text, such as this sentence which says, this movie doesn't care about cleverness, wit, or any other kind of intelligent humor. That's the kind of sentence which traditionally would require a human to say, is this a positive or a negative assessment of this movie? It's very challenging because it's full of very positive words, but then it kind of flips everything upside down with this doesn't. The parse tree you see in front of you was automatically generated, however, with a deep learning algorithm, and the red dots are placed over parts of the parse tree which the computer has automatically figured out are negative in sentiment. And as you can see, this algorithm has actually correctly placed this sentence. It's actually read the whole sentence, and despite the presence of lots of positive words, figured out that this is a negative sentiment. It did this, by the way, being trained on only 11,000 sentences. So this is not big data by any means. This is more like big algorithms. And this is leveraging the kinds of feature learning that I described that Google did, but instead of watching lots of videos, it's leveraging features that came out of reading lots of books. So this kind of natural language processing is also going a lot further. This is a piece from a recent academic paper. If you look at the middle one, this is looking at two different sentences. Pollack said the plaintiffs failed to show that Merrill and Blodgett directly caused their losses, and basically the plaintiffs did not show that omissions in Merrill's research caused the claimed losses. Now if I said to you, are they saying the same thing more or less or not? You would think about it a moment, read the sentences again, consider it, and you would say, yes, I think they are. This deep learning algorithm also did that correctly. This number on the far left is saying, I reckon that these sentences are more or less the same thing. So we're now at a point where deep learning algorithms can understand sentiment, they can understand sentences that mean similar things, and they can even pull out semantically similar sentences from a large corpus of text. This is another recent academic paper. The blue sentences are sentences that the algorithm was given, and the black sentences underneath it, it drew out of a corpus of tens of thousands of sentences and said, I think these are semantically similar. Now you're starting to see why when computers can actually read and understand, it kind of changes the game, doesn't it? Because although you can look at these and say, yeah, I think they're kind of semantically similar too, okay, now do it on 100,000 sentences in a minute, right? This is allowing computers to do human-like things, but at computer speeds. And to then combine these together. And this is now bringing you right up to today. This is an academic paper that's just a month old now. On the left are examples of thousands of pictures that was fed to a deep learning algorithm. On the right are samples of thousands of sentences. The green sentences the algorithm picked as being good descriptions of the pictures. Now what are we doing? We're looking at pictures, we're reading natural language, and we're integrating knowledge. Again, stuff that you and I could do, but now do it on 100,000 images and 100,000 pieces of text. Now do it within 10 milliseconds that something's announced. Do you see, this is really changing the game and bringing human-like capabilities at computer-like speeds and scale. And this is the first time in history that I'm aware of that images and text have been able to be combined in this way. Final example of this kind of amazing recent technology, deep learning technology results. This is an example of what we call a knowledge graph. It's a small section of hundreds of thousands of nodes that were in this graph. The deep learning algorithm was fed this graph, but it was actually missing the red lines. Francesco Giugiardini's nationality and gender. The deep learning algorithm automatically filled in those two red lines, the gender and nationality of that person automatically, by analyzing the whole knowledge graph. You could have done that. You could have programmed a computer to do that with rules, but to have it be able to do it in a way which can operate at scale of millions of connections with errors and missing features and so forth in a general purpose way, that before was beyond us. In fact, every one of these text and image analytics pieces I've shown you, in the last 12 months, only for the first time has a state-of-the-art algorithm been developed, and in every case, it has been based on deep learning. In fact, every one of these algorithms was created by the same person. And so if you think that effectively leveraging machine learning or deep learning is about building a huge team and pointing lots of people at these problems, this is not the way the world's going. The way the world's going is single people are now incredibly powerful because they can teach computers to learn how to do all of these kinds of things. So the particular guy that wrote all of these, a guy called Richard Socher, comes out of Stanford University. And no, you can't have him. He's my co-founder of my new startup, in which we're going to be commercializing exactly these kinds of technologies. Before I go, I did want to point out something, though. A lot of you guys I know work in policy, or you're responsible for large funds of money. I want you to think about something important. The blue areas here are parts of the world where over 80% of the world are in services, employed in services. What is services? Services is doing these kinds of things. What is deep learning good at? Doing these kinds of things. What does that mean? Well, this is human performance at doing those kinds of things. We do actually get better slowly over time. This is deep learning's improvement at these kinds of things, and there is no stopping. As we get more data and more computational speed, deep learning gets better. We actually know that, fundamentally, algorithmically. I think we're about here. Okay, what does that mean in 5 years' time? What does that mean for society, for the economy, for employment? There's a lot of excitement for me about these technologies, but I also want people to think about what do we need to do to make sure that the world is ready when these technologies go even further than they do now. Thanks very much.
So you just can't show that slide and then walk off stage here.
Sorry, Peter. Figure it out, okay?
Come on back, Jeremy. So you and I have had this conversation many times,
yes,
right? I think the numbers that the Martin School at Oxford said is something like 48% of all jobs might get displaced by AI and robotics.
Yeah, you know, they were economists that wrote that, and I noticed that economist was not on that list. I think that they're very short.
You think they're very short on that prediction.
Mm-hmm.
So I guess there are different people of different points of view. Your point of view is, can I just throw out, there's one that says, things, don't worry about it. We've always had technology. We've always been partnering with technology, and the human carbon labor force will continue on with the silicon one. Others are, we're screwed, and others are, we're going to be screwed in the near term, but we'll do better in the long term. Where do you come out on that?
You know, Peter, the interesting thing is people still think about the S-curve of technology you described.
Yeah.
And in some ways that served us well. You know, the Industrial Revolution.
But that's so last year.
Exactly. The Industrial Revolution was like, okay, humans spend most of their time putting energy into processes. Now along comes the steam engine, and suddenly we get to a point where most energy comes from steam engines. But then it did flatten off, right? And it took 50 years or so for the economy to adjust. During that time, there was a lot of poverty, unemployment, social disruption, but it sorted itself out. But now, think about the same thing as disruptive, but which has an exponential capability. So my view is that unless we specifically think about the policy implications of this now, it's going to be very disruptive. If we do think about the policy implications, for example, things like a negative income tax, basic living wage, other ways of distributing wealth that are not based on labor scarcity.
I think they called that socialism or communism back in years past.
I think they call that abundance.
Ah, okay. So we have an interesting ride ahead.
Thanks very much.
Jeremy Howard, everybody.
Bye-bye.